8, 9, 10. Two-dimensional Fourier transform, linking observations with theory. What are we going to do next? We're going to see how to do the computations. The heart of the matter, you have to do the computations before you can do anything. Here is the data set that we are going to do a two-dimensional Fourier transform. And I'm going to make some assumptions that you know a few things. I'm going to assume that you know that time will transform into frequency, omega. That you know that space x, the x-axis, will Fourier transform into another frequency, the spatial frequency, which is also known as the wave number. And I'm also, to answer my questions, you're going to need to know one very basic thing to answer almost all of my questions, and this is what you need to know. This thing here is a shifted impulse function. This is called a delta function. Suppose there's no shift. Suppose it was simply a delta function at the origin. Suppose t0 was 0. What would we have over here? We would have a cosine of zero frequency. Sine of zero frequency is nothing. So we would have a constant. So in the event of an impulse at the origin, the Fourier transform is a constant. And if the impulse is not at the origin, then we have this oscillation, cosine on the real part and sine on the imaginary part. And if you are looking at the omega axis, if you are looking at some plot where the axis is omega, you're going to see an oscillatory function. And what will be the frequency of that oscillatory function? What does it depend upon? Changing t0 will change the frequency of that oscillatory function. Okay, let's see if I can erase the screen and move on. Okay, so here we have our data set, and it's been three-dimensionally Fourier transformed, so suddenly we have three planes to look at. Three new planes. And I've told you already what these axes are. Ultimately, the kind of like this is the ultimate answer for the ultimate one you're going to get, but you'll have these intermediate planes, which will be interesting. Let's hope I can erase this, what I've written on the screen. Okay, there we go. Let's now go to the next picture. Have to click on another. Okay. Now, I really like this topic, and I'm going to tell you why I really like this topic. Because it's the connection of theory to observation. If you're 23 years old, nobody cares how much more theory you're going to learn. You can write Greek letters on a piece of paper forever. What they really want to do is not learn how much. What's important is not how much you're learning, how much you know. What becomes important if you can relate it to observations. This data may cost $500,000 a day to collect these kinds of data sets. And anyone who can add information, add value to this collection operation can do very well. Let me be a little bit more clear what I mean about theory. Theory, it really is. Oh, I'm using the wrong pen here. Drawing with the mouse doesn't. Theory, what it really is some kind of a model that you built. And there are many, many examples for many, many different models, and you'll cook up your own model, and you'll be trying to connect theory, your model, to the observations. Now, many of these complicated models you might build in the real physical world would involve Fourier transforms. And the example we're doing today is the model is only the Fourier transform. Okay, so when you get to be very successful at linking observations to theory, you're going to make lots of money, right? And you're going to donate all that money to the Stanford University Geophysics Department so we can educate more people. Okay, so let's now try to erase the screen and go on to the next slide. We have to go from theory to observation, back and forth through these paths. And let's see what we have in these different planes. Well, the observation is a real-time functions, real functions of space. But as soon as we start Fourier transforming, we get imaginary numbers. And so, for example, these real numbers, the imaginary part is 0, but when we get over here, we got imaginary parts. And so you might say, oh, there's twice as many numbers over here. But no, there should be the same amount of numbers. And so you lose half your numbers because this plane is symmetric. Like, you can see that this blob over here, I should be using the other pin, is matched by this blob over here. There's a symmetry in this kx space. And of course, it really stands out up above. Excuse me, I'm not very good at using this indicator here. It really stands out up above. So that's a normal thing. So that you have really the same number of parameters in this space, and in this space you have really the same number of parameters, because you lose half the parameters because of it being symmetric, but you gain half the parameters because it has an imaginary part. Now the same thing happens down here, except now the symmetry is not about this vertical line. Instead, the symmetry is about this horizontal line. You can't see it very well, though, because the top looks pretty much the same as the bottom. In fact, the top and the bottom are the same. They're made up out of cosine functions, so it forces this real part to be even. If you could see the imaginary part, it would look pretty much the same, except when you went to the negative omegas, which, by the way, are on the top here, when you went to the negative omegas, the polarity up here is going to be opposite to the polarity down here. So what's black up here will be white down here. Black and white. Okay, then you get to the final result when you're in the total Fourier space. There's another type of symmetry. The plane here without anything of interest in it here is matched by the plane here without any interest. And then, of course, you're seeing this interesting line here, which is also down in this space. So how do we do this calculation? Okay, let's start on the let's start up here. We have the second axis. This would be axis 2. For every point on this input data plane, we're going to create another point down here. In fact, it isn't a point; it's going to be a line, because we have time running at any particular x. There's time running down it. And we're going to be doing a Fourier transform of this time. For all x, we're going to do a Fourier transform, a one-dimensional Fourier transform. Remember, you all know how to do one-dimensional Fourier transform. We're going to bring that into the omega space. So the idea of this red arrow is that you have some kind of a loop, a do loop or a for all for every loop, for every point on the x-axis, do a Fourier transform on the time axis, bringing it to omega. And the green guys do the same sort of thing. They just do it in the horizontal direction. It's the same idea. You're just doing axis 2 and 1 instead of 2 and 1 and 2. Okay, so computing the things is easy, but then you get results, and the question is, do you understand them? So now let's see if I can erase this and march forward. Before I march forward, I'll just say that this is often called the FK space, the omega case of x space. And I suppose it is because nobody can type in omega, so they say f. F is for frequency. Omega is just 2 pi. If you define everything in terms of radians, which seems to be what's happening here, if you define everything in terms of radians, both of those things are radians, then your equations don't have to have 2 pi's in them. So the equations are more compact, and that's why we use omega and k instead of temporal frequency in hertz or cycles per second, and what would we use there? Okay, so there's one more thing to tell you about the raw data. That is that there is an instrument, in the instruments on the ship, there is a low-cut filter that tries to remove everything at low frequencies. So this is the frequency axis, and here we are at low frequencies, and it tried to remove everything. It did a pretty good job. It tried to remove everything below 10 hertz. The total range of this axis, the omega axis, this range of omega is 62 hertz, and the reason it's 62 hertz, I'm going to tell you, is that commonly data is collected at 2 milliseconds or 4 milliseconds, often collected at 2 milliseconds and immediately subsampled at 4 milliseconds. What I've done here is I've sampled it at 8 milliseconds. Now, as a consequence of sampling the data coarser, I have a smaller frequency range. I have only 62 hertz. You can look up the theory in a book. Whereas commonly, in the original recording, you'd have 250 hertz, which for processing economies might quickly be changed to 125 hertz. So I've lost half of the possible frequencies. Now, why did I throw away alternate points? And what happened because I threw away alternate points? If I had included all those points at the higher density, I would have had this signal, this picture here would have been bigger, but what would you see out here? You can see everything's getting weaker. It would be really, really weak. Here, I'm not using the right pin here. Forgive my dreadful writing here. It would be really, really weak out there, so then you'd lose a lot of the resolution, which I wanted you to see how far apart these lines were. So they're pretty close together the way it is. So anyway, that's why I made those choices. And so that's it. The next topic we're going to cover is there's going to be a quiz on all these results, these things that you've seen. So let's just stop right here.